So welcome to lesson 4 of the Network Science BVCN tutorial. Last week we heard from Joy, who was talking about network visualization using Cytoscape. And so as kind of the R counterpart to that, I'll be talking about using the igraph package in R this week. And so during this lesson, I am going to mostly talk about kind of principles of visualization. Because we have this nice tutorial in Markdown that I'll show you at the very end that you can go through at your own pace. But just kind of thinking about what a network or what a graph is. When I say graph, so there's a field of mathematics called graph theory that basically is like the formal mathematics behind network science, and they call networks graphs. So if I say graph, I mean network. But we're used to looking at networks already, right? So we might have a network that looks like this, a very simple network. Is this recording? It is? Okay, cool. With 3 nodes. We might think about, okay, how is this going to be represented in a program like R, for example? Well, a common way of representing networks that you've actually already seen in Jacob's lesson, because you plotted networks this way, is to use adjacency matrices. And so, sorry, I'm gonna draw a nice adjacency matrix for this, where you'll have 3 very uneven rows and columns. They're not supposed to be this uneven, but this whiteboard isn't super easy to use. And each row, these are going to need some reorganization. Each row is going to correspond to one of your nodes. As well as each column. And using a matrix like this, you can actually describe your complete graph structure without having to worry about these visualizations that we were doing before. Where if we wanted to describe this graph using an adjacency matrix, we'd say, okay, A and B are connected, so we'll put check marks with A and B and C are connected, so we'll look for B and C. We'll put check marks. And because this is an undirected graph where there's no directionality, it's not A goes to B or B goes to A, they're mutually connected. We have these connections in both places. If you represented this in R as an adjacency matrix, you'd have 1s and 0s. So 0s where there's no connection, 1 where there is a connection. You'll note that we don't have connections along the diagonal because we don't have self loops. And then if you wanted to have a weighted adjacency matrix, that's actually very easy. Where these check marks are, you instead of putting a 1, you'd put the weight of that edge. All right, and so Speakeasy, for example, is going to output an adjacency matrix that you can then import into igraph. What igraph does is it takes this adjacency matrix and will turn it into this complicated network object that then is able to store metadata about all of these vertices and edges separately. And that allows you to do kind of complex visualizations. So that's kind of how the network's stored a little bit. I want to also just note that there's important caveats when you are visualizing a network. And so you're used to probably drawing, for some reason this is the wrong color, there we go. Drawing plots in R or in Excel or in any program that look like this, where you have an x-axis and you have a y-axis, and then you'll have some data, so kind of, and then you can do things like draw a trend line, whatever you want to do with your data, right? I'm not gonna do that. So you'll have a trend line, and so this has a really clear interpretation in space. So if you move in the x direction, that means something, right, in units of x, and if you move in the y direction, that means something in units of y. But when you draw a network, so thinking about our network before, that that interpretation in space no longer is meaningful. So I could draw the exact same network that we had before, above, like that, or like this, just to be really exaggerated. And these two networks are identical. So if we want to label them again as A, B, and C, when you have a graph, the information that you're getting is about binary connections, binary relationships between your vertices, right? And so if we think about a social network, you might think about A, B, and C either being friends or not friends. We could say that A and B are friends, B and C are friends, and A and C are not friends. The distance of A and C in space means nothing. So the top network and the bottom network tell you the network of friendships in the same way, but they look very different. And because of that, it's natural that your eye will interpret this data differently. And so you need to be really careful about that when you are interpreting networks and when you're visualizing networks, so that you're not being misleading or misled. And so there's lots of different ways to kind of lay out your network in igraph, and you'll see a bunch of different layout functions in the tutorial. They'll give you slightly different looking networks. And so you want to be careful about not over-interpreting networks in terms of spatial relationships. So the distance between A and C in two-dimensional space is not meaningful, but you can think about the distance between A and C in topological space, which is kind of how many steps do you have to go to get from A to C. So you have to go 2 steps. You have to go A to B to C, whereas from B, you can just hop directly to C. And so A is essentially a distance of 2 in sort of minimum path length. So that's an important thing to keep in mind when you're looking at networks. The other thing I just kind of wanted to note before we finish here, and before I show you kind of the tutorial, is that so far, we've been looking at networks that are completely connected networks, or at least we've kind of talked about them in our examples as completely connected. So when I mean a connected network, this triangle, for example, is a connected network. You can get from every vertex to every other vertex by following an edge. Similarly, this sort of quadrilateral, because I can't draw a square, is also a connected network. But if you consider all of these vertices together, that is disconnected, right? You can't get from the triangle to the square following an edge. And so we would call these, in network science or graph terminology, different components of the network. So this component is completely connected because you can get from any vertex to any other vertex by following a path. But you can't get from this network to this lonely vertex in the middle. And so when you're actually plotting your networks, you might want to get rid of these kind of hermit vertices in the middle, because they're not telling you anything structurally, right? They're just by themselves. They don't have any interesting information in them. You might also want to represent each of these components separately, so you're not having an overly complicated network, because really they aren't telling you any structural information between the two. A lot of times people just extract the complete component of their network. So there's interesting graph theory that, like, once you have enough edges in your network, you'll get one kind of gigantic component that incorporates most of the nodes. And so if you were in a situation like that, you might actually have one really big component and then maybe some smaller stuff on the sides, as you'll see in our example. And maybe you only want to focus on that really big component, so the largest component. And that's totally okay to do. And so I'm going to stop sharing that. And I'm just going to quickly take you to the tutorial. So I'm not going to run through this, but I'll show you how to make your network using Speakeasy. This is pulled straight from the Speakeasy tutorial. I'll show you how to look at your different adjacency matrices and how to kind of get them out of Speakeasy's output, and then how to turn them into networks, right? And then there's going to be some examples about what can go wrong when you're plotting, right? So here we can see that the layout function accidentally collapsed everything onto a line, so that network visualization doesn't tell you anything. But this is the same network plotted a little bit differently. You can do really fun stuff with putting metadata onto different vertices and different edges, thinking about color and shapes, and you could, I actually don't show you vertex shapes, but you could do different vertex shapes as well. And so that's really going to be your imagination can lead you where you need to go there. There's going to be filtering edges. We can talk about, if you want to get rid of low weight edges. I mentioned kind of the major component, that one big connected component. You can see that pretty clearly in this graph where you have one big super connected component and then lots of smaller stuff. And so then we can, we can lay out our graph differently, like I was saying before, the same graph laid out in very different ways. But here we've just pulled out that big component. We're just looking at that. Then you can also look at the second biggest component. Like Joy was saying in her lesson, you can highlight specific vertices. And because you can assign specific graphical features to nodes and edges, that gives you a lot of flexibility in the types of visualizations you can do, right? So a lot of it's kind of sometimes tedious and by hand to kind of look at specific vertices, but you can do that quite nicely if you want to call attention to specific groups of vertices. Yeah, and so that's kind of what we'll cover this week. Hopefully we'll cover a little bit more of analysis in igraph soon, and then we have some special topics lessons also scheduled. So see you at office hours next week.